Okay, should I start? All right, so I want to now return to the model I began my first lecture with, the Hubbard model. And you may recall recall in my first lecture, I said that the Hubbard model does have a phase diagram that looks very much like this. And that's what I want to show you now. So now even the Hubbard model, I'm going to argue, and this may well be actually true in real life, has three separate phases as a function of doping in its phase diagram. It has superconductivity and many other things, but let's focus here just on magnetism. Just thinking about the antiferromagnetism of the Hubbard model, we're going to find an interesting new phase, the analog of that topological phase. Okay. So here's the Hubbard model written out, and for my purposes here, we want to transform the Hubbard model into a Lagrangian, and so when you go to the time formulation, the Lagrangian has this time derivative term for the electrons. And then this interaction term, by some exact identities, you can decouple into a term of this type. And there's some factor here, I've forgotten, something like 3/4. I may not remember this. This is in some of our papers. So if you put some factor like this, or maybe 4/3, something like this. Yeah, that's more like it. Then when you perform the integral over S, you just get this operator squared. And you just play with some identity, this operator squared is nothing but this operator. Plus some changes to the chemical potential, which I'm not writing out. So this is now a theory where you have the electron field, but you also have a spin field, S, which is conjugated to the electron spin. So this is useful to have because it tells us about broken symmetries. We're interested especially in various antiferromagnetic states. Okay? So I described two states to you in my first lecture, and those states were this just comes from mean field theory of the Hubbard model, depending on the strength of U if you wish. So you could take this axis to be U if you want, but it would be doping in real world. At large U, you have an antiferromagnetic phase and some doping, and then you also have a Fermi liquid phase. Okay, so these are familiar phases that are all available in the theorem. So those are like these two phases here. I should point out there was an error here. That I've written here vortices expel, but actually vortices proliferate here in the short range order phase. So these two phases here are the metallic analog of these two phases of the XY model. Okay? All right, so now I want to get a topological phase. And how am I going to get a topological phase? Well, just like I got a topological phase there, by suppressing certain defects. Okay? So here there were vortices, both odd and even vortices all over the map, and we removed the odd vortices, or we bound them in pairs, and we got a topological phase. So here also you might imagine that there's some defects in the autoparameter, and you could do some funny things to them, and you get some topological phase. Now here the symmetry is a bit more complicated. This symmetry can point anywhere on the sphere. It's not an XY autoparameter, it's a O3 autoparameter. Okay? And the defects of the O3 autoparameter are not vortices, they are hedgehogs, or point defects, not line defects. So that makes the discussion of symmetry a little more complicated. If you wish, you can just by hand say, because of spin-orbit coupling, the spins always lie in a plane, and then you can do exactly what I did there and do it over here. And you will find, as I will show you, a topological phase, the vortices are gone from being proliferating to only even vortices proliferating. And in this phase, topological phase, this is the main result I want to show you. The Fermi surface will still look like this. So there's an amazing connection between whether the vortices are there or not, and whether the Lagrangian theorem is obeyed. That's kind of the main result of my lectures that I'm building towards slowly. Okay, so let me try to show you. So I'm going to do this by a method which seems a bit different from what I did here, but in the end it actually turns out to be the same. And it's a very general method that can be applied for any group, not just for XY. So let's just use it. So what the basic idea here is if you transform to a rotating reference frame. That turns out to be the essential way to do it. So the idea is the following, roughly, physically, that you have some region of the sample, and here the spins are up, down, say we're pointing in the z direction. And over there, they're all pointing in the x direction, up, down, up, down, up, down, up, down. So locally, there is some order. It's just that globally, when you go far away, the order just rotates in a different direction. Now, the electrons, when they're moving around in this region, will see that order. And this will induce them to change the Fermi surface because they are seeing the order locally. But once they get there, they're seeing a different order. So what we're going to try to do is transform to a rotating reference frame. Just like when you talked about motion of a pendulum in the rotating Earth, well, you just go to the rotating reference frame, and then the equation of motion, you don't worry about the rotation of the Earth, you get the Coriolis force. So here we want to do the same thing. What is the analog of the Coriolis force when you're in a rotating reference frame? And in fact, the way to do all this is by introducing a gauge invariance and Higgs field and so on. As you'll see, it's very much, that's what gauge fields are really about. They're about transforming the rotating reference frames. Just a choice of frame. So I have this electron operator on some side, Ci up, Ci down. And I'm going to write it. I'm going to write it in terms of some other fermion, which I'll call psi I plus and psi I minus, times some matrix R. So this is an SU2 matrix, some SU2 rotation. So the 2 by 2 matrix. R is something like alpha, beta, minus beta star, alpha star, and alpha squared plus beta squared is 1. So that's the most general SU2 matrix. And determinant 1 and it's unitary. Okay, so this is a rotation of just the electron operator in spin space. So, so this I'm writing it out this way because this is going to allow me to work in terms of these new fermions. And these new fermions are related to the old fermions by some rotation. So if my autoparameter here is pointing this way, well, I just take those as my fermions. the C in terms of a theory for R and psi. Now, of course, here I had two fields, and now I have, well, I don't know how many fields. So I've introduced new degrees of freedom. Well, this is just like a sigma ij. There it was just plus minus 1. Here, I've got while there have lots of degrees of freedom. And so naturally, when I do this, there will be some gauge invariance, which I have to keep track of. Okay, so now what happens when I do this rotation to S? So let's look at what S looks like. So if you write this out, because that's the other important term. So in terms of this, so S dot C dagger sigma C, you can then write as S dotted into C dagger will be, sorry, will be psi dagger R dagger sigma R, sorry, like this. And this I'm going to write with some identities which I don't remember. This I'm going to write as H. So this is identity equal to this, where I get psi dagger sigma psi. So for this to work out, you can show that you put all the indices, and this is not difficult to show. I just can't get the indices right on the board. What you find then is this new field H is related to the old field sigma S by so it will be, there's different ways of writing it. Sigma dot S is equal to R times sigma dot H and R dagger. Or conversely, you can also write sigma dot H is equal to, just put an R dagger here. So the R dagger R is 1. And sigma recall that actually I wrote here. R dagger R dagger. Okay, so from that you can get these relationships. So I've introduced a new vector field H, which is related to the spin. So S is the physical spin, which direction is pointing on a given side. And H, we can think of as the spin in the rotated reference frame. So H is the electron spin in a rotated reference frame. Okay, and this makes complete sense. So R is an SU2 matrix, and you do some rotation of the SU2 matrix. S is a vector, and this is just some rotation of this vector. And R dagger sigma R is just the rotation SU2 matrix lifted to spin 1. That's the Wigner matrix that rotates in spin 1 objects. That's a spin half rotation. This is a spin 1 rotation. So normally you write this rotation in terms of Euler angles, 3 by 3 matrix. So this is, this relationship is of the form of HA is DAB then SB. This is just another way of writing it out. And DAB is related to R dagger sigma R. And this is the Wigner rotation matrix D, and that's just is just the lift of the SU2 matrix to an SU2 matrix. So one thing you should notice here, and this is crucial, when R goes to minus R, this doesn't change. So that's true because a 2 pi rotation of spin a half is a minus 1, whereas a 2 pi rotation of spin 1 is plus 1. Okay, this is just the rotation of the spin. Okay, so now really everything follows from this. After we have played with this a long time, I guess. But key thing is to keep track of all the symmetries. So there's a lot of symmetries here. There's a local symmetry and there's a global symmetry. And you really have to carefully distinguish them. They're two very different things. And this is true at any time you play with any kind of spin charge separation. You have to keep track of that. Okay, so let's just talk about the symmetry. So there's where should I write it? Maybe no, I don't want to write it there. No, let's try to write it here. So there's a global symmetry, and now we'll call it SU2 global. And what happens under a global symmetry? So the global symmetry is some rotation U. So it's an SU2 matrix. Suppose I do such a rotation. And then what happens under the global rotation? Well, C goes to U times C. And so you notice from here that R goes to U times R. And then from that, psi goes to psi, doesn't change. And then you can ask what happens to H. Now S, of course, transforms into the global symmetry. I won't write it out, but it's something more complicated. But the important point is that the H field goes to H also. And that has to be the case just by looking at this. So this is the term in the Hamiltonian, which is this term here. So it has to be in rotation invariant. It is rotation invariant. So since psi goes to psi under this symmetry, and this is rotation invariant, then psi doesn't change and this can't change either. Alright, so this H field doesn't carry global symmetry. Because roughly speaking, it is the local orientation of the spin no matter what it is. You know, we rotate it to the local orientation, we're just keeping track of it. So it's really measuring the magnitude of the local spin, not the orientation. Okay, so that's global SU2. But there's another transformation. Let me just write it down here, which is gauge SU2. And let's say this is some matrix V. So under this matrix V, what happens? So what is this gauge SU2? Well, the gauge SU2 is something that acts in between here. What happens to that is that under this action of V, let's say psi goes to V times psi. And then R goes to R times V dagger. Over there. And then you see that C goes to C. And you can figure out what H does from this. So H transforms in some, I won't get it right, but let's see if I can figure this out. So sigma dot H is like the lift of the, goes by sigma dot H. Okay, I won't remember which way it is, but let's say V dagger V, something like that. And this is gauge because V can be space-time dependent. It doesn't matter. It can be different at different points in space. This will be a theory, symmetry of the theory. Because everywhere you're writing the physical operator is R times psi, so when you do that, there's an SU2 gauge invariance that we're introducing. So this theory, in terms of H and R and psi, is an SU2 gauge theory. H, because it transforms under the SU2 gauge transformation in spin 1, is the Higgs field. That's why I'm calling it. It's a Higgs field. And R is the analog of phi in the previous part of my talk. It's a spinor. It's a spinor variable that transforms into the spinor representation of the gauge SU2. But it also transforms by left multiplication in the global SU2. So it's kind of a very peculiar beast. It's got both the global charge by left multiplication and the gauge charge by right multiplication. And another way to think about it is that R is two complex numbers, so it's really O4 vector. And so it can transform, it has an O4 rotation that you can do on it. O4 is SU2 cross SU2. One of the SU2s is left multiplication, which is the global rotation, and the other SU2 of O4 is the right multiplication, which is the gauge diagram. Okay. All right. Okay, so that's the thing to keep in mind, and now all you have to do is make this substitution and plug it in here. Just plug this in here, make this substitution also, remove S and replace it by H, and so the general strategy is that your partition function initially was a path integral over C, a path integral over S of some from H, and now becomes a partition function of psi, of R, and of the Higgs field, of e to the minus some Lagrangian here, some other Lagrangian. This is one more degree of freedom, and so this is has a redundancy, an extra path integral you have to do, so it's a gauge theory. It's an SU2 gauge theory. Okay? All right, so let's try to understand these phases. What's happening in these phases here? So, roughly speaking here, so now I'm going to try to draw in a new phase. And the new phase will be the Higgs phase. Okay, so here, and this is going to be very analogous to what I did over here. So in the short range ordered phase, the Higgs field is fluctuating all over the map. So it's 0. And so is the rotation matrix. It's going all over. And here they're both rigid. Here the Higgs field is non-zero. And this is also non-zero, so you have long range order. You don't need to transform into rotation reference frame. R is the same. And this is exactly like happened here and here. So what's up here? Well, up here is a very nice thing. Here the Higgs field is non-zero. So what that means is that when you can transform to a rotated reference frame, and once you transform to a rotated reference frame, the spin is large, because that's H is measuring the magnitude of the rotated reference frame. But R is not zero. R is zero. So this means that the spin operator, which is like H times R squared, if R is zero, this whole thing is zero. So there's no long range order. And what's happening is locally there's order, but when you go somewhere else, the order is pointing in a different direction. So the Higgs field allows you to measure the order in a rotated reference frame. That's what the Higgs field is. It's also what it is in the SU2 theory of weak interaction. It's just a measure of the local order of broken symmetry in a rotated reference frame. It's just that the frame is rotating everywhere, so there's no long range order. You can't measure it. But there is a local order for the Higgs. Okay. But what are the fermions doing? This is the key thing. What is the Fermi substitution? Actually, before I get to that, let me yeah, no, let me see. What are the fermions? Okay, so all I do is I substitute what's here. I make this substitution and that substitution into the Lagrangian. Okay. So what will I get? So I'll get something like C dagger is psi dagger, R dagger, d by dt, of R psi, and then I get minus Tij. So this is these are complicated things. Psi dagger, R dagger, R J, J. The only thing that's not complicated are the next two terms. So it just becomes 4 over Q2 H squared plus H dot psi dagger psi. So I've got this rotating reference frame, and the Higgs field is acting like the local field acting on the rotating fermions psi. But these terms are kind of complicated. And there's a whole technology on how you deal with this. Basically, this term basically for the fermion to hop, since the fermions carry gauge charges, for them to hop, you need a gauge field. So you also have to use a gauge field by Hubbard autonomous decouplings and all of that, but I'm just not going to go there and talk about all the details. Basically, I'm just going to replace this by approximately equal to psi dagger, expectation value of R dagger I, Rj, psi j. So that's the simple mean field of factorization I'm going to make. And then you can argue later on that as long as you're in this Higgs phase, when the Higgs field is condensed, all the gauge bosons are massive for the Higgs mechanism, and this kind of factorization is perfectly safe. Okay, so we just mass out all the Higgs bosons, and so then we factorize this. So this is approximately, going to throw everything away. It's psi dagger d psi tau minus Tij psi dagger I j plus H dot psi dagger. So we have a very important conclusion. The psi fermions, you see the Higgs field as having long-range order. So in the rotated reference frame, the spin has long-range order, provided you look at the rotated fermions. Everything is just completely uniform. H, so in the Higgs phase, H is just a constant. And so what happens is that the psi Fermi surface reconstructs. Psi Fermi surface reconstructs. Now, in fact, this is the same statement that you hear in the theory of weak interaction. In the theory of weak interaction, you say there are some massive direct fermions, the electrons and the muons and the neutrinos. And then you go to the Higgs phase, and the Higgs field is condensed. The Higgs field gives a mass to the fermions. That's the theory, right? Standard model. The Higgs field gives the fermion a mass. And the Higgs condensate makes the fermions massive. Now, when you have a Fermi surface, it's a little more complicated. When we talk about Dirac fermions, they're zero energy excitation only at one point in momentum space. Whereas Fermi surface, they have zero energy excitation on a line in momentum space. That's this. So what happens is that the Higgs field gives these fermions a mass, but not all of them. It gives the fermions a mass at these hot spots I told you about. Okay. So that's why you get a gap, and that's why the Fermi surface reconstructs. So this statement that the Higgs field gives the reconstruct the Fermi surface is really the same statement that you hear in the theory of weak interaction, that the Higgs field gives the fermions a mass. Same thing. Even the equations are all the same. The only thing, the dispersion of the fermion is not relativistic. That's the only difference. And so here, the Fermi surface of the psi fermions. So the psi fermions have a gap, the C fermions also have a gap. What the two Fermi surface of the C fermions is a bit of a complicated thing that I don't want to talk about. And so just schematically, let me say, there's gaps here that weren't there before. for all fermionic excitations. And so the Fermi surface reconstructs. This happens even though they're short-range order. So it's the topological order that has reconstructed the Fermi surface, because H, H of course here condenses, it's not just that it's non-zero, it's of this form. It's -1 to the Ix minus Iy. So it's a staggered configuration of the Higgs field, and that's the order parameter in the rotated reference frame. So all the gauge theory is going to rotate the reference frame, and all the Higgs field is telling you about the local ordering in the rotated reference frame. Okay. It's a very general lesson, and in fact, to me, it's really what gauge theory is all about. They're all like that. All right. So we've shown you that there's this new topological phase where the Higgs field is condensed, and this topological phase has short-range order, but it has kind of a long-range order in a rotated reference frame, and that's why the Fermi, that's sufficient to give the fermion the gap on the hotspots. So this gap opens up at the hotspots because of the presence of the Higgs field. It's sufficient. You don't really need long-range order. The Higgs field is good enough.
But it is defined in not comparable
Sorry?
to the external file. In Higgs mechanism,
Yeah.
and the file must become to the external file. So the Higgs model will become okay.
Yes.
When the external file is cancelled,
External what?
external file is
External fry?
external file is cancelled. So the Higgs model will become gapless.
Yeah.
But in here I
Yeah. So if you remove the Higgs field, this is gapless. It has a large Fermi surface.
But then not see external file coupled this file.
External phi?
Yeah, external like the magnetic file to couple the
External flux? What do you mean? Magnetic flux?
because in the Anderson Higgs field,
Yeah.
the mechanism,
Yeah.
the vector potential, the gauge universe either the phase gradient. So the Anderson Higgs model will get
Yeah. So here there are some gauge bosons which I haven't written out. There are some gauge bosons that come by looking at this guy. So this guy can be written as a phase factor of some gauge bosons. So these gauge bosons have to be there. There's also gauge bosons here. I just ignored them. But those gauge bosons become gapped because of the Higgs field. That's why you can ignore them. Okay? Well, I already made that step. I forgot about the gauge boson. There will be gauge bosons here. And when you treat this term more carefully, and you do some kind of gradient expansion of this in the Higgs phase, you will find there is a gauge boson. But eventually that gauge boson gets gapped because of the Higgs field for the same reason. So in the end, there's also analogs of W and Z bosons here. So there's some high energy excitations. So all of that becomes part of the spectrum of this theory, the W and the Z bosons and these fermions. But now, what makes this theory in some ways more complicated than theory of weak interaction, the fermions are not fully gapped. Even after the account of the Higgs phase, there's still some gapless fermions sitting around because you had a Fermi surface. That's the disadvantage of being a non-relativistic theory. Given relativistic theory, the fermions are gapped and they require mass. Life is simpler. But here, there are still residual fermions that are gapless. But the gauge bosons are fully gapped. So the gauge sector is exactly the same. Okay, so now let me give you, so another, and that will be the last thing before I show you some experimental data. Another picture of why this phase is topological. Okay. So this is a very simple picture, which I will. I think I can do that over there. So let's consider the simpler case where the spins all line up like, okay, just to make connection with the previous lecture. So imagine the spins, the spin field S has a vortex. So here, here's my square lattice. Okay, now one caveat I should say. The spin field has a staggering factor. So I'm not going to draw that out. I'm just going to draw the n field. Imagine n is varying from point to point. Okay. I won't draw this factor. Just think of it as a ferromagnet, although really it's an anti-ferromagnet. So I don't draw the sublattice pressure. So then imagine there's a vortex here, and the spin is pointing like this. So this is the physical, this is what I'm drawing here, is the physical field N. It's measurable, there's an actual vortex sitting there. Okay? So now suppose I had such a thing sitting there. There's a very low energy state in my model, in this topological phase. Remember, for the XY model, we showed that when you went to the topological phase, single vortices disappeared. All vortices were bound. And I'll show you here why that has to be here too. For the case when spins line is playing. So what is the idea? The idea is, oh no, I needed that. Okay. We want to transform the rotated reference frame. You perform a rotation so that n goes back to uniform. Okay? So you want to pick an R. So remember there was this, I won't remember. Okay, look it up. So we know that sigma dot H is equal to R dagger sigma dot S into R. So the idea is for this vortex, we want to choose R such that H equals, let's say, 1, 0, 0, and minus 1 to the Ix plus R1. Okay, let's not worry about this, I just dropped that factor everywhere. So what I want to do, I want to rotate every spin so that it points in the x direction. So this S is looking like this. S has a vortex. I'm going to choose R so that H is a constant. I'm going to go to rotating reference frame so everything is a constant. All right. So let's pick a point here. Let's pick a spin over here, which is pointing in the x direction. Okay. So this I don't have to rotate. And I go around. This one I have to rotate. This one I have to rotate. So R I have to keep choosing with this rotation. When I go around, the rotation for R changes by an angle of 2 pi. Okay. Now what is the rotation matrix for a 2 pi rotation? For spin a half. minus 1, right? So as I go around, R goes to minus R. So if I really try to make the Higgs field content around such a vortex, I find I can't. R will go to minus R. There's no single. I'm only talking about rotations about a single axis. If you choose multiple axes, it's a little more complicated. But for simplicity, let's consider only the plane spins lying in a plane. Then I can't straighten them all out by a single value global rotation. So if R is not simple, so basically this means that there's some cost to create this. And in the Higgs phase, it's a large cost because I have to pay for the fact that R is multiple valued. I have to have some gradient over here. There must be a cut. And which means that psi is also multiple valued. So this means that in topological phase, this is not allowed. There are no single vortices in the topological phase because R is multiple valued around it. Okay. So in fact, in that phase, there are only double vortices if the spins lie in a plane. Now it turns out the case of spins lying not in a plane is a bit more complicated. I can't explain all the topology here. But it turns out that phase is characterized by the absence of monopoles or hedgehogs. There are no hedgehogs in that phase. So it's not completely disordered. It's got a topological order, and there are no hedgehogs in it. So that's the statement here. Vortices / hedgehogs, these are the defects, are suppressed in topological phase. So just like in the toric phase, vortices, and the double vortices are present. Over here, this will be either all vortices, of course, for the XY model. And for the SU2 model, the hedgehogs. It's not much more complicated. It's the case here, a bit more subtle, but I don't have time to go into that. Anyway, so the bottom line, the main message of my lecture is that there is this very general phase diagram of the Hubbard model, just considering antiferromagnetism, where you have a phase without long-range order, phase with long-range order. These are the conventional, well-known, and well-studied phases. But there's also a third phase, which does not have long-range order like this phase, but which has the Fermi surface of this phase. So this is the topological phase. And in fact, for the easy plane spins, this is the same topological order as the toric code. It's a bit more subtle for the SU2 spins, but the same basic picture applies. Right? This is the Higgs phase of SU2 gauge theory. Okay, now let me. Any questions? So that's the end of my lecture. I'm going to now show you some experimental data, which perhaps indicates that this is exactly what's happening. And then in the experiments, which are on the electron doped rates, they vary the electron density. And there's some evidence that they go like this. That there's a small region of electron density where they seem to see exactly this behavior. All right, so questions on what I've talked about so far. I'm going to need the slides.
Question.
Yeah.
What is the vector axis?
What is the what?
What vector axis in your phase diagram?
I don't know. We don't know. All right, so in practice, it's the Stij. So we know from electron doped and hole doped cuprates, which basically differ by the sign of the Tij, the T1, T2, that by introducing some frustrated hopping, you can go, you can go like this, or you can go like this, as you increase doping. But, to know the exact parameters, you actually have to solve the full Hubbard model, which people do by very complicated numerical methods, in particular DMFT and cluster DMFT. So we've been working in our most recent paper, we worked with Antoine George and his group to use the DMFT results to constrain the parameters of the SU2 gauge theory. And that's, we find we can fit a lot of these DMFT results by that, with a limited set of fitting parameters. Yeah, but you need large-scale computation to figure that out. Any other questions?
Yeah, another question.
Yes.
Yeah, the mean value of the R, the operator R is not a Hermitian operator. Okay.
R is the actual matrix, right? Right.
Yeah.
So, so if it's fixed, it's R equals 1, and if it's fluctuating in all directions, its mean value is 0.
Can you say again why you don't allow multi-variables of R?
Well, I mean, you do a lot, I mean, the whole theory has an R at each point in space and time. It doesn't make sense to have a multi-value R.
Okay.
Basically, if you have there will be a cut, and that cut will cost you anything. So this kind of vortex is very expensive. It's not allowed.
So yeah, there is a cut there, right?
Well, but again, once you put the gauge field in, it doesn't matter where you put the cut, there's just some cut. So just like the previous time, just like the sigma ij, I had a line of -1. So that sigma ij -1 is like the cut in R. And there's a flux that in the center that's going to cost you a lot of energy. R is a gauge-dependent quantity, so you can choose the gauge field to put the cut anywhere you want. You need a cut somewhere. Okay. Maybe I could show you some phase diagram before I show you this. Yeah, that I don't really have a phase diagram. All right, well, let me. So this is the phase diagram of the whole doped race. The data I'm going to show you for the electron dope, but this is what I have available. Sorry. So this is doping in temperature, in antiferromagnetic phase, and the superconductivity here. And what happens in electron dope cuprate is the antiferromagnetism comes all the way out here, around 0.14. So this green region becomes much larger. And there's really no sign of this density wave order, so you just ignore it. And the question is, what happens as you go out of the antiferromagnetic, increase the doping, and you go to the superconductor? And the measurements I'm going to show you are above TC. TC is quite small in the electron of cuprate, so you can just work right above it. And zero magnetic field. Okay. So there's been a new set of precision measurements by the group of ZX Chen. And this is yet unpublished. It's a preprint, which I guess probably the first time we'll be talking about it, by these authors here, and at Stanford mostly. Let me just show you the abstract of the paper. So what they're measuring is this compound NCCO, neodymium cesium copper oxide. And so what happens is that as you vary axis with doping density, between x equals 0.14 is where the antiferromagnet disappears. So x equals 0.14 is this point here in our theory. So we would say that this is the point here if x equals 0.14. And what this experiment shows is that there's this region between 0.14 and 0.17 here. So now we know from other measurements that the antiferromagnetism disappears here. And they've very carefully been measuring the Fermi surface over here in the region where there's no longer endurance. And their measurements, new measurements are here at 0.15 and 0.16 and 0.17. And what they claim, and they say, 0.15 and 0.16, there's a gap. They see an energy gap with band folding, with Fermi surface reconstruction, which is exactly what this theory has, the gap over there. gap collapses near 0.16, providing one critical point. So now maybe, they say here, maybe this means that actually long range order is present all the way up to there. Maybe. But other experiments don't suggest that. Neutron scattering and so on just favors the explanation. And if that's the case, then maybe it's topological. So if you can rule out magnetism, then somebody sees topological. So here's a picture from their figure. So that's a better version of the Fermi surface that I've been trying to draw here. And then they look at the electron dispersion along the blue arrow and the red arrow. And along the blue arrow, you see this thing coming up to the Fermi surface, and that's the whole pocket over there. And along the red arrow, you see this dispersion there with a gap. So here's the gap. So that's the Higgs field. Part of the ring. That gap over there is the evidence for the Higgs field. An energy gap at this hot spot, near the hot spot. So that's the data. Let's see. So this data has been around for a few months, and let's see what the referees say. And here's another picture of that gap. And here's the calculation from the Higgs field. You take some parameters for the Higgs phase, and you compute the electron spectral function, and then you see the nice thing here. Of course, this is the theory, and that's kind of thing you get in the experiment. This is in the region. In the theory, certainly there's no long range order. You're in this Higgs phase with a rotating reference frame that's going into different directions. All right, this is very, very new stuff. So I almost shouldn't show you at a summer school, but I can't resist because it's quite, you sound very excited, so let's see where that goes. All right, so thank you very much.
Before we finish the lecture today, and actually the last lecture of Professor Sachdev, let's show our appreciation to Professor Sachdev for using this date from the University of Ghana.
Thank you very much.
It's a pleasure.
Okay, thank you. Okay, I hope it goes through airport security.
Yeah.
Thank you.
I just want to take a picture.
Okay.
เรามาเรียนสั้นเด็กคุยได้เด็ก
Thank you. Thank you. Okay. Any more questions?